Alright, so in this series or single video, depending on how long it takes, who knows, we're going to talk about how to build a real processor inside Turing Complete. It's going to be a simplified version of a real processor for some reasons about the game itself, for some reasons about the processor, but it's a step above LEG, the more complicated architecture that Turing Complete makes you build. And it's the architecture that most university computer architecture courses would teach. So it's pretty popular. As a side effect of that, you can find a lot of resources about it online, which is pretty nice. So I'm not going to go super duper into the details because it's pretty easy to go out on your own if you'd like to find more. So the processor is called MIPS R2000. There are other versions of MIPS processors that get increasingly more complicated. There's R1000, which is simpler, but then there's also R4000, 8000, 10000, and 12000. The R12000 is so complicated that I'm not even sure that Turing Complete could handle it at the moment. So maybe if someone wants to go very above and beyond, they could try that. But the R2000 is pretty simple. And the main reason that we're picking this architecture to talk about is because it's going to introduce pipelining once we get much further into it. For now, though, we're just going to build it as a single cycle machine, which means every instruction executes in one clock cycle. Each clock cycle is one instruction, full stop. Okay, so before we can start talking about building the machine, we should talk about MIPS. So MIPS is an assembly language. It's technically a family of assembly languages. There's a whole different set of versions of MIPS. The one that we're going to talk about is specified by this data sheet. So this is called the green sheet. You can find it online if you want to look at it in more detail. We're not going to focus on pretty much anything in this section. You should be able to see my cursor. So most of this section is just floating point stuff. We're not going to deal with floating point. The circuitry is annoying and not very interesting. Easy to look into on your own if you want, but we're not going to deal with it here. We're also not going to look at the pseudo instruction stuff. That's assembler stuff. We're going to let the assembler deal with that. We're going to ignore it. What we do care about is these core instructions on the left, which we'll talk about in a second, these instruction formats in the bottom left, and then these register names and calling conventions. We care about those for programming, not really for building the architecture, but we still need to talk about them. So, on the left here, you can see MIPS supports all of the normal operations that you would expect: add an immediate value, add immediate unsigned, and add unsigned. You might ask, what's the difference between add and add unsigned, since with 2's complement, addition is the same whether the numbers are signed or not. The answer is that most real processors do what's called overflow traps. So if your program causes overflow, the arithmetic unit will signal an exception to the processor. And the processor goes, okay, do I have a handler registered for overflow exceptions? And if the program specifies a handler, then the processor runs that handler and then goes back to the program. And the handler can do a number of things. Usually it just tries to recover from the error. For overflow, there's usually not really anything to do. So the difference between the add and add unsigned instructions is that the add unsigned instructions cause overflow and the add instructions don't. We're not going to talk about how MIPS normally handles exceptions and traps and stuff like that, because it adds a lot of circuitry and it's not, again, very interesting. But you could find more information about that from the resources from a university course, because they usually do talk about that. So for our purposes, add and ADDU are going to be the same instruction, and I guess we'll allow either of them. It doesn't really matter. Then there's also logical operations, so and with immediate, or, nor, or with immediate. There's more instructions than just the ones here, so there's also XOR with immediate. I believe there's also nor with immediate. And then there's these instructions, these comparison instructions. LEG did not have these. So essentially, you can see over here the specification. set less than compares two registers, RS and RT, and sets the destination register, RD, to 1 if RS is less than RT and to 0 otherwise. So it lets you do comparisons. And you can use the results of these comparisons to do a lot of things. You can use them for conditional jumps. You can use them for regular Boolean logic. So you can like take those set 1 bits at the bottom and AND them together to do regular Boolean logic or all that kind of thing. You can even do Boolean not using set less than. Like you don't need a not operation to do that. So this is pretty powerful. And then, of course, there's also unsigned version. Then we have these shifts. University courses would generally not talk about how to implement these shifts. I think for the sake of simplicity, we're also going to skip it, but it's very easy to add these because Turing Complete has shift components. And then there's memory operations. So MIPS is what's called a load store architecture, which means the only interfacing that you can do with data in memory is through load instructions and store instructions. All of the other core instructions only operate on registers. So store byte lets you store a byte to memory. Store word down here lets you store a word to memory. Store half-word we're going to ignore for our build, but it would let you store 2 bytes at a time. And then there's also load word and load byte. One thing to be aware of is when you are loading a byte from memory, it actually matters whether you want to treat that byte as signed or unsigned, because the registers are all 32 bits, but a byte is only 8. So if you want to treat that byte as a signed value, and the byte is negative, you need to make sure that the 32-bit number you store in the register is also correctly signed. You need to make sure that it's also negative. So in order to do that, we do what's called sign extending. You can check for yourself that if you take an 8-bit negative number, and you extend it to 32 bits by setting all of the top 24 bits to 1, you get the same negative number. And if you have an 8-bit positive number, then of course setting all of the top bits to 0 will give you the same positive number. So that process is called sign extension. You take the most significant bit and you copy it into all of the higher bits in order to extend a number to more bits. And so we're going to have to actually be careful to make sure that we correctly sign extend bytes when we load them. And there's a separate instruction called load byte unsigned, which always does 0 extension. And so in fact down here you can even see the green sheet defines these things. So you can see some instructions may cause overflow. Those are tagged, so over here. You can see sign extended immediate is defined as 16 copies of the most significant bit of the immediate 15, followed by the immediate. This is syntax for a hardware description language called Verilog, which I am definitely not going to talk about in this series. The important thing is just to know what this means. 16 copies of the most significant bit, followed by the immediate itself. 0 extension is just 16 copies of 0, followed by the immediate. And then this other stuff is specific to jumps and branches. We'll talk about that later. You can see there's several different jump and branch instructions over here. And then this last one is about the it's about the store conditional operation, which we're not going to talk about. Okay. So now we can talk about these instruction formats. The instruction formats are down here. These specify how the instructions parts are laid out in the 32-bit instruction words. So you can see all 3 formats start with a 6-bit opcode. And by start, I mean it's in the top 6 bits, so it's actually at the end. And from that opcode, you can tell which format you have, and then you can do further decoding. So these R-type instructions have 3 register arguments, RS, RT, and RD. This shamped field, which is short for shift amount, and it's usually 0. And then a funct field, which specifies more detail about the operation being performed. These I-type instructions just have 2 register arguments and an immediate value, so a literal 16-bit constant. And these J-type instructions are just 26 address bits, and that's it, nothing else. So, with these R-type instructions, RS and RT are argument registers. They are arguments of the operation, and RD is the destination. So if we look at this add instruction up here, you can see it's R-type, and the specification is that the value of register RD is set equal to the value of register RS plus the value of register RT. And then over here on the right, it says what the opcode and funct field should be. So the opcode should be 0, and the funct is 20 in hex, which is, of course, 32 in decimal. And so this column has all that information. On the next page, there's much more detailed list of opcodes and functions, so I'm not going to get super into this list. For I-type instructions, RS and RT are usually both sources, but they don't have to be. Sometimes one of them is a destination. So for example, over here we look at AND immediate. You can see it sets the register RT to be equal to RS and the 0 extended immediate. But over here, branch on equal, which is also I-type, you can see it's using both of them as a source. It compares their value. Okay. Floating point instruction formats we're going to ignore because we're not talking about floating point instructions. Pseudo instructions we're going to ignore because that's the assembler's job. So the last thing to talk about on this page is registered names. So MIPS lets you refer to registers by number. So you could write, and 1, 2, 3, and that would mean and the values of registers 2 and 3 and store the result in 1. Notice that the destination came first, even though in the instruction format it comes last. I don't know why they decided to do that, but they did. So focus on the assembly syntax, not the instruction format, because as you'll see when we build the decoder, we really only have to worry about the instruction format for a single circuit, and then we can just forget about it. But you need to know the assembly syntax in order to actually write code, so focus on the assembly syntax. So if we wrote and 1, 2, 3, it means and the values of registers 2 and 3, store the result in register 1. And over here we can see what those things are. So register 1 has an actual name, which is $AT. They all start with $, so I'm not going to keep saying that. And its use is the assembler temporary. What that means is that you shouldn't touch it. You should assume that the assembler is using it to put intermediate values when necessary, and you shouldn't touch it because you have no clue where the assembler is going to insert things that might change it. So don't touch that one. V0 and V1 are registers for functions to return their results in. You can also use them as temporaries when not calling a function. A0 to A3 are for passing the first 4 arguments to a function. Then there's a bunch of temporaries, registers 8 through 15. Then there's a bunch of saved temporaries, and we'll get into what that means later when we talk about how functions work in MIPS. Then there's a couple more regular temporaries, 2 more registers that you shouldn't touch because they're reserved for the operating system. We're not going to talk about an operating system, but we're still going to follow the calling convention. And then there's these 4 special registers. So we'll get into why the global pointer is useful on the next page. The stack pointer holds the current address of the top word of the stack. So if you load the word which is pointed to by the stack pointer, you're getting the top word of the stack. The frame pointer is similar to the stack pointer, and we'll talk about that more when we talk about how functions work. But for the most part, most programs no longer use frame pointers. Compilers generally optimize that out now, so you don't really have to worry about it. And then the return address is a special register for storing the address that the current function should return to. And sometimes you actually just want to save this value on the stack, and then you can use the return address register as an extra temporary. So that's everything on this page. And then just a warning before we move on to the next page, it's much more data dense. So looking over here, there's a whole bunch of stuff that we don't care about. So we don't care about anything under this line. We don't care about exceptions at all. These are useful if you don't know them, I guess. Memory allocation is useful, so we'll talk about that. Floating point stuff we're going to ignore. Data alignment is exactly what you would expect. So there's byte alignment, half-word alignment, word alignment. We're not going to worry about double word alignment. That only really matters if you're dealing with floating point stuff. And then the other thing to be aware of is that MIPS is a little endian architecture. So what that means is if you have the address of a word, 4 bytes of data, but you load a byte from that address, the byte that you're going to get is the least significant byte of the word. So the one that comes first in memory is the least significant byte, whereas if you were to write them out on a piece of paper, the one that comes first would be the most significant. So just be aware of that. And then over here is a table that lets you convert from MIPS opcodes, the thing in the first 6 bits, and funct fields, the thing in the bottom 6 bits, to actual operations. And you can just ignore the third column completely because it's only for floating point. So over here, you can see if the opcode is 0, then nothing appears in this first column. And the reason is because when the opcode is 0, we instead look at the funct field to figure out what to do. And those are for R-type instructions. So you can see if the opcode is 0 and the funct is 0, since this is the 0 row at the top, then the operation is shift left logical. If the opcode is 0 and the funct is 2, then the operation is shift right logical. Opcode 0, funct 3, the operation is shift right arithmetic, etc. This goes all the way down. There's a few jumps in here. There's also a few things that we're not going to worry about. So we're not going to worry about multiplication or division, these operations. We're just going to pretend they don't exist. We're not going to worry about any of these things. These are called traps. We don't care about them. Similarly, we're not going to worry about any of these. These are various stores and coprocessor things that we don't care about. We're not going to implement these. These are basically more traps. These things are related to multiplication and division, so we're going to ignore them. And then we're not going to implement mov-z or mov-n, which are called conditional moves. So they're like copy instructions, but they only copy the data sometimes. And I'll talk about extending the architecture with those at the end for those who are interested. What we will implement is pretty much everything in this column down to about here, with a couple of exceptions. And definitely all 8 of these, or yeah, all 8, the first 8 things in this column. And then also these, which are just regular arithmetic and logic. And so we'll refer to this table when we build the decoder. The other useful information on this page is this memory allocation. So MIPS specifies that you should have a full 32-bit address range. But then it also specifies that user programs, which is what we're concerned with, are not allowed to use the top half. So the top half of the address range is reserved for the operating system. So the user program address space ends at hexadecimal 7FFFFFF, and that C is because this is the address of a word. So the last F would be the address of the topmost byte. And down here at 0 hex is more reserve space, so you can't put data down there. The text segment is where the program is stored. We're not going to model that. We're going to keep our program in a ROM because TC is better equipped for that. So our program data is going to be completely separate from our actual manipulable data in memory. And that data is the static data and the dynamic data. And also technically the stack, but we can ignore that for now. So static data is supposed to be data that is initialized before the program starts. It's initialized by the operating system when it starts the program. Like I said, we're not going to worry about an operating system, so we're just going to treat the static data as more dynamic data. The dynamic data is supposed to be data that you don't know about when you write the program. It's data that's going to be computed at runtime and then stored and manipulated by the program. Since you don't necessarily know how much of that you're going to need, you get this structure that's called a heap, which is essentially memory that's been allocated for use by the program, attached to some metadata that the operating system has for allocating more of it. And as you request more and more dynamic data, the operating system gives you more and more addresses moving upwards. So starting, you can see over here at hexadecimal 10008000 and growing upwards. The stack is the function call stack, just like you would have seen in leg, but instead of having its own component, it just goes in data memory. And the stack is the opposite of dynamic data. Instead of growing up, it grows down. And the reason for that is to allow you to use all of this dynamic memory space if you need to, even though there's two things occupying it. So eventually they'll crash in the middle, but if you're not using a lot of dynamic data, that means you have a lot of stack that you can use before they crash, and vice versa. So the stack starts at the top and grows down. Now the problem is, this means we need a lot of addresses in order to, get this whole thing in TC, right? We need almost a full 31 bits of address space, almost. And TC can't handle that. So instead what we're going to do is just map a subset of this address space, mostly around the relevant numbers, like these and at the top. And then we'll just make the computer crash if you try and access memory that's outside of that range. That's just a restriction from the game. That's not really any conceptual barrier between what we're going to build and the real machine, hopefully. So, okay, hopefully that's enough about the instruction set. I'll talk more about programming in MIPS assembly once we actually have the machine and we can make it do things. I personally don't think there's much point in talking about it now, but if you'd like to look into it, you can pause the video, go Google MIPS assembly simulator, and you'll find like 10 of them online, and you can look up the syntax and try writing some simple programs. So, okay, now on to actually building things, which is what most people are here for, I'm sure. So, first, even though leg makes you build an ALU, I've seen a lot of, let's say, questionable ALU designs in TC before, and so I want to talk about the sort of standard way to build a large ALU. And by standard, I mean this isn't going to be the most efficient circuit for this, but it's the normal technique, and the most efficient circuit would just, use a better subcomponent. So the first thing is you don't want to use separate adders for addition and subtraction. The reason is adders are expensive circuits, and if you use efficient adders, then they're actually even more expensive. So you really want to make sure that you can do addition and subtraction in one circuit, and part of the reason that we use 2's complement arithmetic is because it makes it easier to do addition and subtraction in the same circuit. So over here, you can see that by using XOR gates, we can conditionally toggle the second argument, the B argument, and change from addition to subtraction. So this is, the game sort of tries to push you towards this a little bit, with the level called bit inverter, but I think it's pretty easy to miss that this is possible and just switch straight to using a byte negator instead of a byte XOR. So yeah, that's the first thing. Big XOR gate. The second thing is you can separate out the logic and the arithmetic. You don't have to do them together, and it's actually a bit easier if you separate them because conceptually it lets you keep the things further apart. So we can use a 4-way multiplexer, and we'll build one of those in TC in a little bit. You can use a 4-way multiplexer to control the different logic operations, and over here you can just see the table of MIPS control bits to operations. So 0 is AND, 1 is OR, 2 is NOR, this little prime over here means not, and 3 is XOR. So we'll implement that. And actually, why don't we just go and do those first? So let's switch to Turing Complete over here and go to the component factory. I don't know what's open right now, so just ignore whatever this is. And let's see. Okay, so let's start by talking about multiplexers. I think I already have some. Okay, so first let's talk about a two-way multiplexer for single bits. I actually have one of these already, but we can build again. So remember the multiplexer level, which asks you to do this for whole bytes. We want one that just works on single bits. So, you know, very standard. I shouldn't have to go too much into detail about this circuit, but you have the control signal. You also want its inverse. And then the result is either not the control signal and the first data line, or yes, the control signal and the second data line. And then, since only one of these ands can be true at a time, we can just wire them together like this. So this is a 1-bit, two-way multiplexer. So 2-way Mux2-1 for 1 bit. And you can build a version of this that scores better in Turing Complete by not using AND gates, but we're not going to worry about score for this because the memory is going to completely screw the score anyway. So then the question is, how can you chain a 2-way multiplexer to get a 4-way multiplexer? We're going to need some nesting. So, starting with, let's see, here's the multiplexer we just built. Starting with multiplexers that are 2-way, how can you build a 4-way multiplexer? Well, the trick is that you actually need 3 of them. The idea being, we have 4 inputs now. So this is input A, input B, input C, and input D. There's still only one output. It's a 4-to-1 multiplexer. But now there's 2 control signals, right? So there's one that controls the less significant bit, let's say, so select 0. And there's one that controls the more significant bit. Let's call that select 1. And so now, if I want to pick this one when the control is 0, this one when the control is 1, this one when the control is 2, and this one when the control is 3, well, let's look at the bit patterns and see what you notice. So we want to pick this one, 0, 0, this one, 0, 1, this one, 1, 0, and this one when the control is 1, 1. You can see that the bottom bit is just alternating 0, 1, 0, 1. So if we connect these two to one multiplexer, and these two to one multiplexer, and make these multiplexers switch when the low bit switches, like this, so we want both of them on the same control signal, then ignoring the top bit, we're correctly selecting between these, right? So when this bit is off, we'll pick this one, or this one. And when this bit is on, we'll pick either this one or this one. And then it's just a matter of correctly selecting between those 2 options based on the top bit. So we want to select the bottom option when the top bit is on, the top option when the top bit is off, and that's easy, that's just one more multiplexer, like this. And so this gives us a 4-way 1-bit multiplexer, so Mux4-1. And then we can make the component preview look a little bit nicer, and then for shape, we just stick some buffers in the corners here, because buffers are free. That changes the shape of the component in the game. I actually don't want these pins there. I want these pins in those tiles. Do it like that. There we go. So that just moved these pins over at the top. So this is a 1-bit 4-way multiplexer, which, as we just discussed over here, we're about to need. So now let's build this circuit. So this is a 1-bit logic unit, and we're going to call it that. So you can see I already have a big MIPS ALU over here, but for now we'll just make logic unit 1, which means 1-bit logic unit. And what does that do? Well, let's see. It takes 2 control inputs, R0 and R1, and 2 data inputs, X and Y. So let's set up those, and we can just put them all right next to each other like this. So we have X, we have Y, R0, and R1. Okay. And so now, what are the 4 operations that we can do in order? We have AND, OR, NOR, XOR. And we have gates for all of those things, so we can just plop those right down, put them over here, AND, OR, NOR, XOR. So, without looking at the control signals, we can't know which value we're actually going to need, of course. But this is one of the major things about hardware, which TC really, I think, doesn't emphasize enough. The most efficient hardware circuit for a problem where you're not 100% sure which problem you need to do in advance is usually a circuit that does all of the problems in advance and then picks the right one later, as opposed to a circuit that tries to pick out what it should do in advance and then only does that operation later. Those circuits tend to be smaller, they're usually easier to organize, and in real life they also tend to run faster and consume less power. So we're going to stick with that general idea. And actually I need nesting here because we need the multiplexer that we just built. Not that one. It's probably not visible because of that bug. No? Am I just blind? Oh! No, that one's on nesting 2, so I need to be on nesting 3. Yeah, there it is. Okay. There we go. So we're going to pick the correct output with a multiplexer. And so you can remember AND was 0, OR is 1, NOR is 2, and XOR is 3. So they're already in the right order. So all we have to do is plug these in to the output bits on the multiplexer. And I'm not going to worry too much about clean wiring over here because this circuit's so simple. Although I will for this. And then these 2 are on the wrong side of the component, right? We put them at the bottom because that's what the schematic says, but we actually need them to be up here on these 2 pins. So we're going to have to wire them all the way through. It's not a big deal. Let's send them along up here, using straight lines because it's a bit more organized. And now let's see. This wants the higher order control bit on the right. We have that one on the bottom. So these are going to have to cross here. So there's the multiplexer select. And then for the actual logic operations, we just need to get one of them all the way down here. And again, straight lines to stay organized. The other one over here. So this is our 1-bit logic unit, and if we just move this whole thing over 1 tile, nope, 2 tiles. Yeah, there you go. Now the display is a bit nicer. Okay. So this is a 1-bit logic unit. It performs all of the MIPS logical operations with the correct control signals. So now let's take a step back and let's build this circuit, the 1-bit adding unit. But since this part is so simple, we can actually just do that at the same level as our 1-bit ALU. So our 1-bit ALU combines 3 control signals, 2 for controlling the logic unit, and the addition unit, and then the 3rd signal to select between logic and arithmetic. So here you can see the entire control table. You can see we don't have specified operations for 0 or 1. The reason for that is because if we go all the way back and look over here, you can work out that that bit controls whether the operation is signed or unsigned. So that doesn't affect what the ALU is. That doesn't affect what the ALU itself is doing, so we can just leave these. And then over here, yeah, so control is 2, we're doing addition, control is 3, we're doing subtraction. Notice the only difference between these is even and odd, so that's going to be controlled by control 0, which is the bit over here that controls the XOR gate. Pay attention and notice that control 0 does not set the carry into the full adder. The reason is because this is what is called an ALU slice. It's intended to be chained together with a bunch of other ALU slices to build a full 32-bit ALU. So we actually want to get the carry in from the previous 1-bit slice, and we'll use that control 0 line to set the carry in on the first slice, the one that's attached to bit 0. So let's go ahead and just build this whole circuit. So we're going to want ALU1, no, come on, and we need nesting 4 because we need a logic unit. You can see I have way too many components over here. No, that's the full one. Okay, here we go. So here's a 1-bit logic unit and a 1-bit full adder. And so what does the schematic say? The schematic says take an XOR gate, put it by pin B. So let's do that. Can just take a bit more space, that's fine. And then it also says we need several inputs. So we need X, Y, actually, let's do it this way. We need X, Y, and 3 control signals. So usually where we get from 2 to 3 is when I'll switch from using single bits to packed bytes. So we'll call this control. And then that one we want to split with a byte splitter. And then, as we saw in the diagram, the bottom bit is just going to run around. These bits are going to go straight to the logic unit. So we'll worry about that guy later. And that should be up here. And these bits are just going to go straight into the logic unit. Like, nope, not like that. Like that. Okay, there we go. And so now we can worry about this adder. So the schematic says control 0 should control whether or not the XOR is toggling input B. So there we go. Input A, it says, should go straight through to the adder. Note the adder doesn't care about which bit is the carry in because they're all 1 bit, so I'm just not going to worry about that. And speaking of the carry in, I forgot that there's another input here. Ah. This, I guess. Fixing wiring mistakes in TC is sometimes really annoying. Okay. There we go. That's better. Actually, let's do it that way. There we go. That's better. Okay. And this last bit here is the carry. Okay. This is input X. This is input Y. Do this that way, it's a bit cleaner. So input X goes straight to the adder and straight to the logic unit. Input Y goes straight to the logic unit, but it goes to the adder through this XOR gate. And then the carry in goes to the adder directly. The outputs of the adder are the sum and the carry out. According to the schematic, the carry out should just go straight out of our slice, but the output needs to get multiplexed. So we'll put 2 output pins over here. I see that wire. So this is the output, the result, and this is the carryout. So the carryout, according to the schematic, can be connected directly to this pin. Now the output of the logic unit and the output of the full adder need to be multiplexed. So for that, we can use the two-way 1-bit multiplexer that we built. Just stick that right here. And of course the control signal goes on the wrong side again. It's fine. Okay. And so now when this control signal is off, that means we're doing either operation 2 or 3 because it's the high bit. So if it's off, we're doing the lower numbers. So then we want to pick from the adder. So I always build my multiplexers that the lower number inputs are closer to the select signal. That way I don't really have to worry about remembering it. So this one goes at the top, and then the logic unit output goes at the bottom. And so this is a nice, fairly clean, except for this wire, which I can, clean up a little bit more. There we go. So this is a nice 1-bit ALU slice, and this does all of the same things that a bigger ALU would do. We just have to chain them together. The important thing to note here, the biggest thing that I see people seem to get confused by, there's only one adder here. You only need the one adder because the XOR can control whether or not you're doing subtraction. And then the other thing is I want the component to have a nice shape, so we stick a bunch of buffers here. We use buffers because they're free, like I said. And so this gives our ALU components a nice shape. Okay, so now how do we connect these together? We connect them like this. So you can see they should all share their control signals. So that's completely free. The lowest carry-in is the bottom control bit. That just changes whether we're doing subtraction or addition, if it matters. If we're doing logic, then the carry-in doesn't do anything, right? Because the carry-in bit doesn't go to the logic unit. And I know I'm going fast, but the hope is that people will go at their own pace and slow the video down and watch things several times if they have to. Don't feel like you need to keep up. I know I go fast. I'm not too worried about it. Then each 1-bit ALU slice outputs a single bit of the final value, as well as a carryout. We're actually going to use this carryout here. So don't think of the carryouts as just being something that chains to the next adder. Think of them as useful data in and of themselves. So let's build this thing, and for the sake of demonstration, because TC has bigger components and for performance it's better to use them, let's just only build, let's say, a 1-byte version of this, and then I'll show you the full version that I have set aside over here already. So let's build an ALU 8. So that's an 8-bit ALU. And let's just hide some of these things that we don't need anymore. Should be fine. And then here I need to use ALU 1, so I need nesting 5. Oh, and the game crashed. Oh, okay. And it's updating. Alright. Here we go. Once it gets there. Low production quality, sorry. That crash is actually pretty consistent, so I could have avoided that one. Oops. Go back to MIPS, ALU 8. Now it'll work, so I need nesting 5. Okay. can't move. Yeah, there we go. Alright. So, this is just going to be a 1 byte ALU. So we're going to have an X input, a byte, a Y input, a byte, and a control input, which is only 3 bits, so we'll split off the ones that we care about. I tend to use green for control signals just out of habit. When I have 2 data inputs, I like to use pink for the first one, purple for the second one. I have a scheme generally that I try to stick to, so this color is usually addresses, which we'll see soon. Okay. So then what does our diagram say we should do? It says we should split off the individual bits and then start chaining these 1-bit ALUs together. So let's do that. Let me move these down one so that I can fit the byte splitters a bit better. Like that. That's the Y input. This is the X input. And now we want to take our ALU1 and... oh, I don't actually need to split these. We just want to chain 8 of these together. So 1, 2, 3, 4, and actually, you know what, let's turn them on their side. Just because that'll be a little bit easier to lay out. Give myself some more space. Don't split this up. And I need to leave a gap for the carry wire to fit through. So, okay. This is actually slightly awkward that the carry in is over there. The carry out is over here. I can make it work. Okay. So the carry out chain needs to ripple around the ALUs like this. So actually, if I get rid of the ALUs, I can just copy this thing and paste it several times. Then I can put the ALUs back. I missed one. So you should try and copy-paste whenever possible, just because it reduces the chance that you make mistakes, right? As long as the thing that you copy is correct, everything that you paste will be correct too. That's just sort of generally useful, helps reduce the number of mistakes that you make. Okay. And then actually I did need to split this off. I was right the first time, because this bit sets the lowest carry in. Sets that. Okay. And then this is not 8. So actually I need another one of these. So a little bit more copy pasting. Okay. Now these, just to make it a little bit easier to lay out, I'm going to move them up here. And notice I said that this was the bottommost bit. So to get a little bit more space, let's move this like that. And now we want to run some wires all the way across. So this is the lowest bit of the purple input, all the way down to the highest bit. And then the pink input. And we'll change the lengths of these wires later. Okay. So the lowest bit is on the left. That's the one that is getting its control signal from the bottom over here. And actually, I need this gap to be 1 bigger, because I'm going to have to fit the control signal through there in a second. So now let's just connect up all the wires. So this is the bottom bit, and it takes the Y input from this pin. So this one goes here, and then this one is the second bit, the third bit, the fourth bit, fifth, sixth, seventh, eighth, and then the X input, same thing, just comes from higher up, like this. and then we can get rid of all the parts of these wires that we don't care about, like that. So that's nice and clean. And then we just share the control signals between all of them like this. So they all get the same control signals. And then we need to combine the outputs into a single byte. Super easy, single byte maker. Take my output color. Oh, except these are backwards, because of course they are. Okay, so give myself 8 rows of space then. I'm not going to worry about the component shape for this one, because I'm not actually going to use it. So let's put the lowest byte on the top, and then use the next row down for each bit, which of course doesn't fit because of where I put this thing. Now it fits. Come over here. So what I just did there, moving this one down a row even though I didn't need it, this is in case I move the byte splitter later. I won't have to move all of these wires in order to, you know, attach a horizontal row to this one. You should try and future-proof your circuits like that whenever possible, because it really makes your life easier. Life gets really annoying if you don't do that. Okay. And then notice this last carry out isn't connected to anything. That's going to change in a second. Now we have a 1 byte output. This is the result of the ALU. So you can just leave that labeled output. There's one other thing that real ALUs tend to have, which the leg ALU doesn't, and I personally think that's a mistake in the design of leg. I think it makes the design simpler. And that is... Oh, I thought I had a slide for it. That is what are called flag bits. So, normally, in a computer, you wouldn't have a whole separate unit that looks at X and Y and compares them, if necessary. You would use the ALU to do those comparisons, and the ALU will set several things called flags that tell you information about its result. So one of those flags, which is particularly easy, and we can just do that right over here, is called the 0 flag. And what does it say? It just says the result of the ALU operation was 0. In TC, it's super easy to check that, right? You just take this byte, and you can compare it to 0 really easily with a byte equals, but that's not free. You can do it for free by taking this byte splitter, wiring all the pins together, and then attaching one of them to a NOT gate. And so if this is true, then the value on the byte wire is 0. So we can send that straight to the 0 pin. So this is a very simple example of an ALU flag. It gives you some information about the result, in this case that its value is 0. Another useful flag is called the sign flag, or sometimes just the negative flag. MIPS calls it the negative flag, so I'll stick with that. And so this says that the result, interpreted as a 2's complement binary number, would be negative. And so how do you tell that? You just look at the most significant bit. If it's on, the number is negative. So that's another easy one. The last one is a little bit more complicated, but this flag tends to be very useful in practice. This is called the overflow flag. So overflow tells you that the result of the computation that you did is definitely wrong. It's not the only way that the result can be wrong, but for signed numbers, at least, if the overflow flag is on, then the result is always wrong. But the overflow flag is also useful for some comparisons, and we'll talk about that as we get deeper into this. So the overflow flag should be set if the sign of the two inputs is the same, but the sign of the result is different. So conceptually, if you add 2 positive numbers, you should get a positive number. If you add 2 negative numbers, you should get a negative number. if you add two numbers with the same sign and the result sign is different, then the answer is certainly wrong, right? You can't add two positive numbers and get a negative number. So we could do that by comparing this bit and this bit and this bit. The circuit for that takes quite a few gates, and it's a little bit annoying to build. I will show it because I did it in my full ALU, but for the purposes over here, we can do the simpler trick, and I'll leave it to the interested viewer to check that this actually works. But all you have to do to find the overflow bit is compare the bottom carry in, the top carry in to the top carry out, and XOR them. So if these are the same, then there's no overflow. If they're different, then there is overflow. And of course, that's exactly what XOR checks. So this is the XOR flag. And we can test that super easily. Let's see, input 2 is addition, and let's just put in some numbers that should cause overflow. So here, if we use a signed representation, you can see I'm adding 64 and 64. The result I'm getting is negative. The overflow comes on. You can also see that the negative flag came on. So this is a full 1-byte ALU with flags, and you could build your leg ALU like this. I wouldn't recommend it. Can I actually show my leg ALU? I think one of the recent patches might have broken it. No, I can't. So my leg ALU looks like this. You can see I did the same thing with XOR to get the overflow flag. That's this one. But it's pretty easy to open the logic unit and just do it inline since it's so small. Anyway, that's enough of that. Back to this one. So I'm not going to give this one a nice shape because we're not actually going to use it. I just wanted to show how you would build it. And we can make this do other things too. So let's put those inputs back to 64s. So if I put it on 2, it's doing addition. If I switch it to 3, it's going to do subtraction. Excuse me. So now you can see that the result is 0, and the 0 flag has come on. If instead of 64, I make this 32, 64 minus 32 is 32. Back to addition, 96. And none of these turn any flags on, which is correct, of course. If I switch this control input to logic mode by turning on this bit, then we can see logic control 4 is AND, if you remember. So 64 and 32 is 0, their bits don't overlap. But 64 and 96 is 64, so that appears to be working. We can put it in OR mode, and we get 96. If we turn this off, we still get 96. Correct, of course. We can put it in NOR mode, so of course that just took the last result and inverted it completely. And you can check with the side panel over here that we are getting the expected results. I'm not going to go through it in a lot of detail. And finally, we can put it in XOR mode. And this is also, of course, the correct value. We can check that it also works for bits that are both on, and that bit is off in output. So this is a correct MIPS 8-bit ALU. What we actually need is a 32-bit ALU, and of course, extending this to 32 bits is possible, but like super annoying. You can see it's not very NAND healthy either. And it's bad for delay because of this big ripple. We're not going to fix that, but what we can do instead is we can use these 64-bit components and just combine them together, still use multiplexers to pick the right one. But we are going to have to build the bigger circuit to check the overflow flag because we won't have access to the top carry-in. So I can show what I did over here, and I gave it a shape like what you would usually see an ALU look like in a schematic diagram. So down here, just remembered I have to fix this, because that should have been connected to this one. Down here, we have the Y input, or the B input. Up here we have the X input, or the A input. This is the overflow circuit, which I'll talk about in a moment. But down here is where the interesting stuff is happening. So this is a 32-bit logic unit. It's exactly like the one that we just built, but it's 32 bits instead of 8. Or instead of 1, I guess. And then over here, we have a single 64-bit adder. You can see it's getting its carry in bit from the bottom control bit, same as what we just did. The A input comes straight through. The B input comes from this 64-bit XOR. And what I'm feeding as the value to that XOR is the byte 255 and all of the top 4 bytes of this 64-byte wire. And the reason that it's just the top 4 is because we're building a 32-bit system. So whenever we use 64-bit wires, we're only going to care about the top 4 bytes. We're basically never going to touch these pins at all. And if we did touch them here, that would be a problem, remember, because that would cause the XOR to flip all of those bits on the A wire, which are zeros. It'll turn them into ones, and then the result from the adder is going to be weird. So we don't want to do that. Then, just like we did with the 1-bit ALU, we use the 4s bit to multiplex between the results, so picking either logic or arithmetic. And then we do this byte splitter thing just that we can make sure that if for some reason this is set by an addition, we don't carry that byte to the output. Why is this 96? Oh, because of this bug where these are taking the inputs from the other thing. Okay. Alright, so then we have our flags. So the flags are exactly the same, just like I just showed. This Z is a little custom component that I have, which just does exactly the same thing that I showed in the 8-bit ALU. Just takes a byte, wires them all to a NOT gate. So the output comes on only if the input is 0. I also have an NZ component. I'm not sure if I'm going to need that in this build, but just for the record, this is exactly the same thing, but it checks for not 0 instead of checking for 0. Over here, we have a negative flag. You can see it takes the top bit of the output, and remember, 32 bits, so the top bit is the top bit of the 4th byte. So we take the 4th byte, we take the top bit. If that's on, the number is negative. And then here we have the overflow bit. So this is actually a slightly optimized circuit. I got this from Altrag, I think. It's in one of the channels in Discord somewhere. The basic idea is we want to compare the top bits of the A and B inputs with the top bit of the output, which we have right here, as discussed. And we want to check if the 2 bits of the input are the same, but the output is different. And so normally, to check that 2 things are the same, you would use XNOR. So we would take this, XNOR them, and then you would also have to XOR these bits with the top bit and check the logic. This is a slightly more complicated circuit that does the same thing, but it has the same cost as a single XOR gate. So this is just to demonstrate that you can, in fact, check the overflow flag, in TC at least, with the same cost as if you use 1-bit slices without using 1-bit slices. So anyway, this is our whole 32-bit ALU. It doesn't do anything more complicated than what the leg ALU would do, other than the flags, but it is nicer organized, it's a clean build, and it, of course, has the flags, which are going to be useful. So that's all for building an ALU, I think. This is the ALU that we're actually going to use for the MIPS build. We should only need 1 of them. In the schematic, for some reason, there's 3, but 2 of them just have the control bits hardwired to add, so we're just going to use a 64-bit adder, because we have those. In a normal circuit, you would have to, build an adder again every time you want to use it, and since you already built an ALU, I guess it makes sense to just reuse the ALU. Anyway, so let's go back to our slideshow over here. So we've done this. We're not outputting the carryouts, but we are outputting the output bits, which is what we care about. So now let's talk about memory. So if you'll remember, We talked about this on the first page, or on the second page of the green sheet. TC cannot handle as much memory as MIPS says that we should have. So instead, we're going to build some custom RAM components, use those to get enough data memory for our purposes. So over here, you can see we're going to have these addresses mapped to with however much memory this is. I don't know, 128 kilobytes of memory for static and dynamic data, and then 64 kilobytes of memory for the stack, which should be more than enough for anything that you want to do with this inside TC. And again, notice that the stack goes all the way to the top of the user addresses and grows downwards. So we want to make sure that the addresses that we map go from somewhere in the middle to the top, and not from the lowest possible address that the stack can have, because we don't know what that is, right? The stack just grows down until it crashes into static data. We don't know where that will happen. And indeed, it might happen in different places for different programs, so we can't build that into the hardware at all. The other thing that we want is we want our data memory to be byte addressable, which means we want to be able to give it an address that refers to a specific byte of memory as opposed to a specific word or even double words, since Turing Complete generally uses 64-bit wires for bigger things. But because MIPS has store byte and store word instructions, we want to make sure that the writable memory is byte-writable or word-writable. And so what that means is that even though we want to read whole words at a time, we want to make sure that it's possible to write only a single byte without overwriting the rest of the word that that byte is contained in. Hopefully that made sense. And so we're going to have to do a little bit of work to make sure that that happens. And so the last thing is, if we start from 256-bit memories, you'll remember from Turing Complete, those have 8 address bits, and they output a single byte. So that's sort of good enough. The problem is we want to be able to read and write whole words at a time. So we actually need to be able to read 4 bytes at a time or write 4 bytes at a time. And so the way that we can do that is by stacking 256-bit memories and using 4 of them at the same time. So I'll get into that. And then in order to build these sets, we need some custom 16 kilobyte memories. These are not very interesting, so I'll just show them quickly. First, just to save some space, it's useful to have this little wrapper around the 256-byte RAM, because this component is way smaller than the actual RAM component, and you're never going to be able to see the interesting data anyway. There's just too much data, so I didn't worry about making sure that the memory was visible. Actually, out of curiosity, I haven't looked at this yet. What happens if I do this? Oh, nothing. Okay. So this is 256-byte RAM. Then we can take 8 of those and combine them together to get this 2 kilobyte RAM. So what's going on here is each one of these 256-byte RAMs is looking at the lower 8 address bits and using that to control where inside its own 256-byte RAM it's looking. But then we select the correct 256-byte RAM component by using the next 3 address bits. So you can see we have a high address and a low address and a high address. And we use the high addresses bottom 3 bits over there to control which RAM unit we're actually looking at. So only one of them will ever be active at a time. Each one of these has a load port and a save port, 1 address, and a 1 byte save value, which, as discussed, 1 byte is exactly what we want. So just to quickly talk about the wiring, we use the same bottom 3 bits here. 1 decoder is to control the read. So here's the the read pins on the RAMs. The other decoder controls the write pins on the RAMs. And don't worry about this buffer, it's just there for shape. And so this lets us build a RAM component that allows for simultaneous writes and reads. It turns out that that's not really important, and so you can actually simplify the wiring here quite a bit by only using one decoder and just attaching the load and write pins together. I think originally this design had separate read and write ports, and so that actually mattered. Anyway, so the wiring here is a bit more complicated than it needs to be. If you are following along and building this circuit yourself, definitely only use one decoder. It'll make your life a lot easier routing, and this is pretty hard. And then the last thing is this save value, which is on the cyan line. Just goes to every RAM, and only the correct RAM will have its write pin turned on. Oh wait, actually no, what I just said wasn't true. You can't simplify the routing, because sometimes you don't want to save. You want to load, but you don't want to save. That's why these decoders have their disable pins attached. Right, okay, oops, ignore what I said. I will try and put something up on the video that says I was spouting garbage. So yeah, these decoders have disable pins. If the load pin is off, we disable the load decoder. If the save pin is off, we disable the save decoder. The load wires are pink, the save wires are purple in this case. And then we wire all of the RAM outputs together, because 7 of them will always be 0, and then the other one is the one that's actually being loaded from, so that's fine. You could use a whole bunch of byte wars if you wanted to, but this is clean. So this is how you make a 2 kilobyte RAM. Now you can combine 8 of those together to make a 16 kilobyte RAM, and the layout is exactly the same, just with a different size RAM chip in the middle. And then the other thing to be aware of is that we use the middle 3 bits of the high address instead of the bottom 3 bits, because the bottom 3 bits are being used inside the 2 kilobyte RAMs. So this gives you a 16 kilobyte RAM component. You could keep going further than this. At the moment, there's a bug in Turing Complete that will make the game crash if you try and go too far. So I just stopped here. And then at this point, I built the MIPS data memory that we want. So it loads up. This thing is kind of a beast, and the exact details don't matter that much. If you want to build along, you can literally just copy this circuit. Nothing here is especially magical except these numbers, which I'll show in a second. The main thing is, remember I said we were going to have 3 sections of memory from over here. We have 2 sets mapping over here and 1 set mapping for the stack. But there's 12 16 kilobyte RAMs here. The reason for that is because we wanted byte-writable memory. So each of these RAMs only outputs a byte. It doesn't output a whole 32-bit word. And that was desirable because they also only write a single byte at a time. So the trick is that for any word address, we have this top RAM up here. For some reason, the circles don't spin on the RAM components, so I'll use this instead to highlight. This top RAM is always byte 0. You give a, we'll say, 32-bit address to the data memory down here, and if you mask off the bottom 2 bits, what you have is a word-aligned address, right? An address that's divisible by 4, which means it's the address of a 32-bit word. That 32-bit word contains 4 bytes, and we arrange so that the low byte is always in this RAM, the 1 byte is always in this RAM, the 2 byte is always in this RAM, and the high byte is always in this RAM, not deleting a wire. High byte always in this RAM. And there are several good performance reasons that you would want a better alternative to this, but for now, this is what we have, so This is what we're going to use. Later, once we get into pipelining the architecture, the fact that 64-bit RAM has delayed loads, you can see that the load pin in the top left of that is a delay pin. Once we get into pipelining, that won't matter, and so I can show how you would switch to using these instead, and that'll be a bit more performant, hopefully. Anyway, so the main idea of this design is that this column on the left has the stack addresses that we're mapping. So this handles these addresses from 7FFF0000 to 75Fs, 7Fs. This one handles the bottom 64 kilobytes of data. So that goes from 1 7 zeros to 1 0 0 0, no, to 1 0 0 1 4 zeros. And then this column just gives us a bit more data memory, mapping 1 0 0 1 4 zeros to 1 0 0 1 4 Fs. You probably don't actually need this much memory for the MIPS programs that you're going to write, so if it would make it easier for you to lay this out, you can feel free to just like trash this column entirely. It's not needed. Then we have our 4 byte outputs, because we read whole words at a time. And finally, we have this one little extra thing. So normally, when you look at a data memory or a cache, you wouldn't see a pin for this. This pin just tells us that the requested address doesn't exist in our data memory component because we're not mapping the whole 31-bit address space. In the architecture, we'll attach this to one of these halt components and make the computer crash if you try and read or write to an address that doesn't exist. Obviously, in a real full MIPS computer, you wouldn't have to do that, but it's pretty simple, so we do it here. This gate is just a 3-way NOR. There's absolutely nothing special about it. So okay, on to the implementation. So I talked about the design, how this is laid out. So the first thing is we need a way to identify which of these 3 sections the address actually belongs to, if any. And like I said, when talking about the 1-bit ALU, we really don't care about performance here, so I'm using 64-bit equals, just like completely without caring. We can figure out which section we're in only by looking at the top 2 bytes. Right? So if we look back at these addresses, you can see whenever we have a 164 kilobyte section, we have all of these bottom 4 hexits for addressing, and the top 4 are constant. So in the first of these sets, the top 4 are always 1000, and we have the bottom 4 for addressing. In the second set, the top bits are always 1001, and we have the bottom 4 for addressing. So that means we can literally just compare those 2 bytes to the constant that identifies each segment, and that's exactly what these do. So this is the constant for stack addresses, right? Top bits 7F, 7FFF, and then this is for the bottom part of static and dynamic data. So top bit is 1, top byte is 10, and then 00, and this is the second section. So 1001. So now each of these yellow lines through the column will be on only if that column is the active one. So the yellow lines are the activation lines. You can see they just go straight down, and then they go into the 3 NOR. So if none of them are on, that means our address isn't mapped, and we turn on this pin. The rest of the complication is for making sure that we are always enabling the correct RAM. So you can see in the bottom left, we have write word and write byte pins. So we have word writable and byte writable memory, but there's no load pin. So as long as you're giving an address, the data memory is going to output a number. And in the actual architecture, we'll control whether or not we care about the number that it's outputting. But that's not a job for the data memory, that's a job for the architecture. In a real computer, that would absolutely be a job for the data memory, which would actually be a cache, not the whole address range. that's like more complication than we care about. So we're not going to deal with that. We'll just always output the data and control whether or not we use it in the architecture. I want unsigned numbers right now. So yeah, we take our address up here in the top left, and then we do what I talked about to split off just the middle, or just the top 2 bytes over here. And again, we like never care about these bottom 4. Then this bottom byte is special, because remember, each one of these rows corresponds to one set of bytes. Whenever you have a word-aligned address, the bottom 2 bits, are always zeros. And whenever you have a byte-aligned address, they might not be zeros. So if you want the second byte of a word, you want the bottom bits to be 0 and 1, where the first byte would be 0, 0. So what that means is we can pick which address to go to inside the 16 kilobyte RAM using only the word address. But then we pick which 16 kilobyte RAM to use with the byte address. So we can do that by just grabbing the bottom 2 bits, throwing them into a decoder, and then this OR gate corresponds to the first row, this OR gate to the second row, this OR gate to the third row, and then the routing got a little bit weird, so to keep it clean, this one points the other way, but you can follow this wire all the way down here, points to the fourth row. Okay. So why are these OR gates? Why don't these wires just go directly through? Well, remember, these are being used to control writing, not reading. So the question is, when do we want to write to, say, this RAM, this one right here? We want to write to this RAM whenever we are doing a whole word write, in which case we don't even care about the byte address, we only care about the word address. Or we're doing a byte write to this top one. So the decoder value goes into an OR gate that says, hey, the byte being addressed is byte 0 of the word. The other control line is the write word control line. So if write word is true, we turn on all 4 of the OR gates to say we're writing to all 4 bytes, as you would expect. Right. So then, since these 16 kilobyte RAMs, each of them is considering only the word address and not the byte address, they don't care about the bottom 2 bits, right? They don't need to know about the bottom 2 bits. That's being handled over here. So we throw away the bottom 2 bits by throwing them into a 2-place shift right, and then we take the bottom 2 bytes off of that, because remember, we're only getting 16 bits of addresses here. And in fact, the 16 kilobyte RAM only handles 14 bits. So we get our high address over here, our low address over here, and we just have to route those through to all of the RAMs. You can see the low address comes from the 1 pin, the high address comes from the 2 pin, and then those are routed up the left column, and then across straight through each row. They're routed across the top row, and then straight down each column. There we go. I made this a while ago. Alright. So that controls the addressing for each of the 64-bit RAMs. The last thing that we have to control is the writing. So each one of these can only write a single byte at a time. So we need to control which one we're writing to. That's these OR gates. But then we also need to make sure that we're writing to the correct column and that we're writing the correct data. So if we're writing a whole word at a time, we want to write all 4 of these bytes. And we want to write them in order: the low byte to here, the high byte, or the second byte to here, the third byte to here, the fourth byte to here. But if we're only writing a single byte with the store byte instruction, then if we're storing to let's say we're storing to the third byte of a word, the assembly instruction that's storing the byte, it should not have to know or care at all which byte is being stored to in the RAM. All it should have to care about is the value of the byte. And that means that the value is always going to be in the bottommost byte, because the value in the register, for example, if the byte is 255, the value in the register is going to be 255, not, you know, hexadecimal FF, 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 just hexadecimal 000000 FF. So that's just the bottom byte. So we need to make sure that when we're in byte writing mode over here, that the write data that we send to the RAMs is not the high bytes, but rather always the low byte. And so over here we have 3 multiplexers, which select between the relevant high byte, or if the right byte line is on, the low byte. You can see the low byte comes around the top here and down the side. And then of course the top row always wants the low bytes, so that just goes straight over there, and then the multiplexer outputs go to each row. So this is the first byte across the second row, the third byte across the third row, and the fourth byte across the fourth row. And so that gets us our byte addressable writing. When the write word pin is on, then these multiplexers select the regular bytes. So no multiplexer for the first byte, but the second byte will go straight through this multiplexer, same for the third and the fourth. And then the last thing we need to do is enable the write pins of these RAMs. So we need to make sure that when writing a word, all 4 write pins in the relevant column are on. When writing a byte, only the correct row has its write pin turned on. So these OR gates are telling us exactly which rows should have their write pins turned on, assuming that they're in the correct column. So all we need to do is 3-way AND. Are we in the correct row? Are we in the correct column? And should we be doing a write at all? So, because, you know, of course, maybe we're in the correct row and column, but we're only supposed to be reading data. So this OR gate tells us if we should be doing a write at all. It's just the OR of write word and write byte. And this wire, let's see, I can change the color to highlight the whole thing. This wire goes everywhere. Right? So this wire goes to all 12 of these 3-way AND gates. And then this wire, so this is for row 0. This wire controls these 3 AND gates, but none of the other 9. And then each one also gets an input from its relevant column enabler, the yellow lines, right over there. So that tells us exactly when we should write to each of these 16 kilobyte RAMs. If the word enable is on, all 4 of these OR gates turn on. I can show that. So you can see all 4 of them have turned on now. And so we will correctly write to the entire column at a time. So this gives us a full word read RAM with a word write port and a byte write port all in one. And so when you build a component that's as complicated as this one, you never want to just drop it in an architecture and hope it's correct. You really want to test it. Oops. You want to make sure that it does what you think it does. So I've hooked up a little thing in the lab over here for testing this one. And I'm not going to show my tests for all the circuits, but you really should build tests for every circuit. For some reason, this one's behaving strangely. I've hooked up the watch state, but I guess the watch states are probably still bugged or something. What is this one connected to? Huh? I am so confused. That's not what I did. Okay, there we go. Anyway, I hooked up the watch states, but for some reason it doesn't like them, so I'm just not using expects in here. Just check it by hand. We have this 64-bit program with a counter that's incrementing by 2, so we can use the first 64-bit word to control the address, and the second 64-bit word controls the write data. And since the data memory masks off the bottom 4 bytes, I'm just sending the whole word through. And we can also use it to control the word write and the byte write pins. And so we can use a test like this just to check that it actually does what we think it does. So over here, this is the address of the top word of the stack. I've put in these assembly codes just for the control bits that I'm using for the data memory. So we send the address of the top word of the stack. We tell it to store the word, whatever that value is, FFFF. So if we go through the first tick, you can see the bottom 2 bytes of that word come on. We're looking at the same address on the second tick. The bottom 2 bytes of that word come on, but these 2 stay unchanged. Now on this tick, we're going to store byte to the same address, but we're going to store FF00. Now remember, when we're storing a byte, we only care about the least significant byte, which in this case is 00. We don't care about the FF. So when I tick this, the bottom thing turns off. But I could change this, right? I could make this AA, and again, this byte has stayed entirely on, as 255, because this AA in the store byte does not affect anything except the addressed bit, or the addressed byte exactly, and the addressed byte is this bottom. Then this address is only here so that we can see the results on the wire, otherwise they would go away. Now we move over. So this is an address right at the bottom of the dynamic data. We're going to store this word, which is not a particularly interesting word, but there, you can see that works. And now we're going to store a byte, again, with some data at the top that we don't care about, and the least significant byte is the only thing that should change. And correctly, that is exactly what happens. Then we try address 0 just to make sure that correctly it is not mapped. So you can see the unmapped pin came on. There's no point trying to write and read anything there because it won't work. Now going over here, this is the bottom of the static data segment. We just try storing bytes to, so this is to test the byte addressability. So we can store to the bottom byte, to the next byte, to the byte up after that, and to the following byte up. And you can see that all of those writes worked without modifying the other 4 bytes. So this is a pretty strong indication that this component does what we think it does. I would highly recommend writing more tests, some more rigorous tests. If you're particularly eagle-eyed, you might have noticed that these tests don't actually test one of the columns in the data memory, right? These tests only cover columns 1 and 2, but there's a whole nother column. So if you just copy these tests, maybe the 3rd column doesn't work. So I would highly recommend writing big test suites for all of your components. Make sure you're 100% confident that they do what you think they do, otherwise debugging gets really, really annoying. And so with that, I think that's going to be enough for this first video. We covered a lot of the intro to MIPS, building some important subcomponents. The only real complicated subcomponent left is going to be the instruction decoder. And once we have the instruction decoder, we can actually sit down in an architecture and just put the whole thing together. And we can actually take a look at the schematic for that. So we really have all of these pieces already, except for the instruction decoder over here. I know this text got a little bit hard to read when I copied the picture over, because I had to make it quite a bit smaller. But basically, this shape, these trapezoids, are just multiplexers. The register file we still have to talk about. So I take it back, the instruction decoder is not the only thing left. Actually, I have a register file. No, I don't want to talk about it. This has gone long enough at this point. We have the data memory, we have the ALU. These ones are just adders, we'll use adders for that. We have 4-way multiplexers. These are just extended to be 32 bytes wide, but 32 bits wide. But that process isn't very interesting, so I'm not going to show that. You do the exact same thing that we did, but with a 32-bit multiplexer instead of a 1-bit multiplexer. These are also multiplexers. This is a shift left by 2, but we have a component for that, so, easy. This is a sine extender. We will talk about that when we build it, but it's so easy that it doesn't deserve its whole custom component. We'll just do it inline. We have instruction memory. That's just going to be a ROM. I'm going to do it with a file ROM, but you can do it with a 64-bit ROM if you'd prefer. I wouldn't recommend that because Turing Complete's assembler is not powerful enough to handle MIPS assembly, but you could do it, I guess. And a program counter. We have those. We just set a counter to increment by 4. Super duper easy. This control type thing, this is just a multiplexer that handles jumps and branching, so we'll talk about that as we build the decoder over here. And yeah, for the moment, this is our end goal. This is a single cycle MIPS machine. So yeah, thanks for watching. If you have any questions, you can put them in the comments or DM me on Discord. I know I went really fast, so you can watch the video again, slow it down, focus on the individual parts, and I'll make sure that there are chapters on the video so that you can find the relevant sections easily.